Hi, Mishler Math students. This is your geometry teacher, and we're going to review something we had before. You might remember the first thing I gave you was definitions. Remember the Daffy Duck definitions? Okay. What we defined, we defined gurgles and glomules. Okay. Now the gurgles, we came up with a definition. A gurgle is a round blob with one eye and three tails. That's a gurgle. Okay, round blob with one eye and three tails. It doesn't matter what glomules are. In fact, we can just kind of erase glomules because we're not going to talk about those. What we're going to talk about today is the relationship between definitions and logic. Okay? Now, we talked about before, if I were to rewrite this whole thing as a conditional, remember, it says, I would say, if it has, or excuse me, if it is if it is a round blob with one eye and three tails, then it is a gurgle. But can I say the same thing the other way around? The converse of that? If it is a gurgle, then it is a round blob with one eye and three tails. Now let's identify these parts. Okay, a round blob with one eye and three tails. That is the P. Okay, the hypothesis. Okay. And by the way, don't ask me why it's P and not H. I don't know. I didn't make up these rules. So now we have a round blob with one eye and three tails, and that's the P here. Okay? And give me a pink. How's that? So gurgle, it is a gurgle. Okay? This is the conclusion. Okay, that's Q, okay, or the conclusion. There, I can. That's perfect. Don't argue with me. All right, gurgle. This is the Q, or the conclusion. Okay, so up here in this first statement we have P implies Q, and down here we have Q implies P. Okay? Notice that both of these are true. If it is a round blob with one eye and three tails, then it is a gurgle. And if it is a gurgle, then it is a round blob with one eye and three tails. And so P implies Q, Q implies P, and so we have what we call a biconditional. A biconditional is when it's true in both directions, okay? A conditional is true whether the conditional and its converse are both true. And we write that like this, P and Q. And we say this, P if and only if Q. Okay? P if and only if. Remember the conditional says if this, the hypothesis, if P, then Q. Okay? And the converse, this is a conditional, okay? the converse says if Q, then P. Okay? So what we're saying here in a biconditional is it's true in both directions. Both the conditional and the converse are true. Okay? And that means we have a definition. A definition is when both the conditional and its converse are true. Okay? And if we make an Euler diagram, which we ran out of room, so I'm just going to go ahead and let me just kind of get rid of this stuff here. And maybe I can... No, that's not the way to do it. I guess I'll just have to clear this thing. Okay. So, alright, let's look at an Euler diagram. And I said that a gurgle this was a gurgle, and one round blob with one eye and three tails. One eye, three tails. Okay. Over here, we have one eye, three tails, and gurgle. And both of these are true. Okay. So using the Euler diagram, and EULER diagrams, that's what these are. I think I may have told you they were Venn diagrams or not. They're Euler diagrams. So using the Euler diagrams, we can actually create one like this, okay, that says gurgle, or GUR, gurgle, and round blob, one eye, and three tails. Because really, this circle goes out to the edge of this, doesn't it? Because there aren't any things with there aren't any round blobs with one eye and three tails that aren't gurgles. And there aren't any things with one eye and three tails that aren't gurgles, or there aren't any gurgles out here that don't have one eye and three tails. So anyway, I don't know if that makes sense to you, but that's how it works. Okay, Euler diagram. You say a gurgle has a round blob with one eye and three tails. So having said that, let's look at this next thing. This is this is from your book, okay, Activity 2. So let's look at how we use this stuff in geometry, because you guys are always going, oh, when are we going to use this stuff, you know? And an important concept of geometry is adjacent angles. Now, we've already worked on definitions of adjacent angles, so this should be review, but take a look at what this says. These are adjacent angles, okay? And these are not adjacent angles. Now, why aren't these adjacent angles? It looks to me like they don't share a common side. Why aren't 1 and 3 adjacent angles? Once again, they don't share a common side, okay? And ADB and ADC, they share a common side, DA, ray DA. However, if you take a look at this, one of them is inside the other, isn't it? ADB is this one right here, and that's inside ADC, the bigger angle. Finally, 1 and 2, angles 1 and 2 don't share the common vertex. And then angles 1 and angle 2 are not in the same plane. They're two sides of the Great Pyramid of Khufu or Khufu. I forget the name. Anyway, list the adjacent angles in the figure at right. Well, it looks like 1 and 2 are adjacent, 3 and 4 are adjacent, and 4 and 5 are adjacent. 5 and 3 are not adjacent. 4 and 2 are not adjacent. Okay? So what do adjacent angles have in common? Can they overlap? Of course not. Okay? No, we just talked about that up there. If they overlap, like ADB and ADC overlap. Okay? So look at what it says. It says angles that do not overlap have no interior points in common. Use this fact and your answers from steps 1 and 2 to write a definition of adjacent angles. And I am going to put this as a question in the questions. Thank you very much, and we'll see you in class.